Today we are doing part 2 of section 5.8. We're going to talk about the inverses of the hyperbolic functions. So a couple of things about the hyperbolic functions. One, they're not periodic. So they're not periodic like regular trig functions. We call them trig functions, but they're not periodic. Some of their behavior is like trig functions, but they're not periodic. So all of them except y equals cosh x and y equals sech x are 1-to-1. So they have inverses. And if we restrict the domain of these two appropriately, we can come up with inverses for cosh and sech. So just like we do for sine and cosine when we define the inverse sine and inverse cosine, we restrict the domain. And because the hyperbolic functions, they're defined with exponential functions, what would you expect their inverses involve? Logarithms. So the inverses involve logarithms. So I want to give you a list of the inverse hyperbolic functions, the definitions, and I will show you. We'll go through an example of how you find the inverse of one particular hyperbolic function. Go through one. I'm not going to go through all of them because it can get a little tedious. But there is a nice in the example that we do. There is a nice trick that we use it's good to remember. So our definitions, let's go to our definitions. I had a professor when I was in college that he loved definitions. He said, when you make this your definition, nobody can touch you. Meaning we define this thing, if we do our definition properly, then basically you're set. If you have a good definition, then you're set. All right, so our sinh, inverse hyperbolic sine, is a very nice logarithmic function. And our domain, I'll just do a table of the domain, is minus infinity to infinity. Cosh, inverse hyperbolic cosine, is a natural log of x plus square root of x squared minus 1. And the domain is from 1 to infinity. Inverse hyperbolic tangent. And the domain minus 1. Cotangent, inverse hyperbolic cotangent. Just a little bit different with the arrangement here. And we have a different our domain is a union here. Secant inverse. So these functions, you can see they're getting kind of messy, they're kind of complicated. And we have 0 to 1 here. And finally, cosecant inverse. Graphs, the book has graphs of these on page 380 something. Let me check here. 388. And this table is listed in your book as well. I just wanted you to if you want, you have it in your notes as well. Page 388, graphs. And table on page 387 of these functions. So what I want to do is I just want to go through coming up with the inverse of one of these functions from the definition of the function itself. All right, so everybody good with our definitions? So we're just listing the definitions. This is what these functions are. When we're working with functions, we often want to use their inverse functions, and it turns out that inverse functions have some interesting applications. They come up in some interesting places. All right. So let's go through finding one of the inverses. So we're going to say f of x equals, let me go back here really quick for a second. Okay. F of x equals e to the x minus e to the minus x over 2, which is which hyperbolic function? Sinh. So this is sinh x. I keep wanting to put a C there. All right. So how do we find an inverse function when we're given a function? What is it? Switch x and y, and then solve. Right. So when we write this, y equals, just getting rid of the f of x notation, e to the minus x over 2, and then we're going to switch. So we're going to say x equals e to the y minus e to the minus y over 2. All right. So how are we going to solve for y? Multiply by 2. So we get 2x equals e to the y minus e to the minus y. What do we do now? we would end up with a natural log of this quantity. We don't want that. So there's a nice little, you know.
Let's just use divide each side, well, the right side by that.
There's a nice little trick to use on equations like this. So, and this type of thing comes up fairly often, so it's good to know this trick. We're going to multiply through by e to the y. So I'm going to multiply everything by e to the y. And now I get 2x e to the y equals e to the 2y minus 1. Anybody see now why we did that? Now what can we do? Add the 1. Yeah, we have this x in here, so that makes it. So what I'm going to do, let's go the other way. I'm going to put everything on the right-hand side of the equation. So I get e to the 2y minus 2x e to the y minus 1 equals 0. Sorry, this should be 2y, e to the 2y. Sorry. There we go. Now do we see why we did this? What kind of equation do we have? It's a trinomial. I don't know that we can factor it, but what can we always use on a quadratic trinomial? We can use a quadratic formula. This is quadratic in e to the y. And this 2x is just one of our coefficients. So we, if I say that u, I'm going to make a substitution, u equals e to the y. I have u squared minus 2x u minus 1 equals 0. And I just have a quadratic trinomial, and I can apply the quadratic formula. So I'm going to plug this into the quadratic formula, use a quadratic formula, and then we end up with, I'm not going to go through the steps, but everybody see now that we can do that. We can plug this into the quadratic formula. I get that e to the y equals x plus or minus the square root of x squared plus 1. And then finally we can take the natural log of both sides, and we get that y equals the natural log of x plus the square root of x squared plus 1, and we use the plus so that we're not plugging, so we're observing the domain restrictions of the natural log function. We have to have a positive argument for the natural log. So that little trick, when you have this e to the y, e to the x, and then the e to the minus x, and you're solving, multiplying through by, here where we've multiplied through by e to the y, that comes up often enough that that's a good thing to have in your little bag of tricks for solving equations. So we would do similar things for the other hyperbolic functions to come up with our inverses. So that's a nice little technique there. All right, so questions on what we did there? All right. Differentiation and integration. We can differentiate, we're doing calculus, so we want to find the derivatives and we want to find the integrals of these various inverse hyperbolic trig functions. And these formulas are also listed out on page 389. So what I want to do, I just want to list out the formulas. If you want to write them down, if you want to copy them down, you can copy them out of your book as well. I'm just listing the formulas so you have them available. And then we'll go through one example of finding one derivative, so you see the process of finding the derivative of these inverse trig functions. So for all of these, we're saying that u is some function of x. And this is the part of this that really not that exciting to me, is we're just kind of listing, here's what they are, here are these formulas. But I just want you to have seen these things. So the derivative of the inverse hyperbolic sine function. And I'm just going to go through and list these. Now, as we write these down, you might notice something. Some of these look a little bit familiar. And I definitely do not expect you guys to memorize all of these. So looking at these formulas, what do they kind of look like? Anybody recognize any of these quantities? They look a lot like the inverse trig functions. A lot of them are the same formula except for a sign change somewhere. So what you want to keep in mind is, if you are looking at some kind of integral, you're evaluating an integral, and it looks like an inverse trig function but not quite, it might be an inverse hyperbolic trig function. Now you can always go through and get your result by trig substitution for any integral that involves quantities like this. But if you recognize some of these as an inverse hyperbolic trig function, you can save yourself some work. Yeah.
Tangent inverse and cotangent inverse.
They are the same. Yeah, that's a kind of a little bonus here. So our integral, when we do our integral formulas, rather than 6, we end up with just 3, because some of them are repeats. All right, so on the in the other column, I'm going to just list some integral formulas. So the integral of du over and I'm writing these in the logarithmic form. So the plus sign is for the inverse hyperbolic sine, and the minus is for inverse hyperbolic cosine. So if we're looking at the natural log, if we have a plus sign, it would be inverse hyperbolic sine, and if we had a minus sign, it would be the inverse hyperbolic cosine. And the minus sign is, did I have a minus sign? I think we should have a plus or minus. Let me double check on that. I think I might have missed a plus or minus there. And the integral of du over u square root oh, I'm sorry, this one, this is either inverse tangent x or inverse hyperbolic cotangent x. So we don't have a plus or minus, because this works for either one of these, because these two are the same. And for this one, the minus sign is for, you end up with the inverse hyperbolic secant of x, and the plus sign is for the inverse hyperbolic cosecant. So these are the logarithmic forms of these inverse hyperbolic functions. With the plus sign, it's inverse hyperbolic sine. With the minus sign, it's inverse hyperbolic cosine. These two are the same, so this is either one of those. And for this one, the plus sign is for inverse hyperbolic cosecant, and the minus sign is inverse hyperbolic secant, just in logarithmic form. So again, I'm not expecting you to memorize these. Just be aware that when you have some integral that looks like it could be an inverse trig function, but it's not quite the right form, it might be an inverse hyperbolic trig function. And then you, hopefully, like I said yesterday, that rings one bell, and you think, oh, there's a formula for the integral of inverse hyperbolic trig functions. Maybe I can go find that, or Wolfram alpha. So let me go through one of these, finding the derivative. I'm not going to go through the integral formulas. One example of finding the derivative of the inverse hyperbolic sine function. So is everybody good on the table if they wanted to copy from here? It is also in your book. Okay. We have y equals the inverse sine of u. So I'm going to write inverse hyperbolic sine of u, sorry. I'm going to use the definition of the logarithmic definition of the inverse hyperbolic sine of u that we just came up with. So we know that y equals the natural log of x plus the square root of x squared plus 1. We went through the process of figuring out that that was how we define the inverse hyperbolic sine of u. So I would take
Are you using x?
okay, this should be x. X I could put u here. So we'll just use x rather than x being a function of u. So I'm just going to take the derivative of the natural log of x plus the square root of x squared plus 1. And I would use what I know about derivatives of logarithms, end up having to do some algebra and some cancellation. But this is where the formula comes from. When I take the derivative of this quantity, it takes a few steps, some simplification, some algebra, and I end up getting 1 over the square root of x squared plus 1. So our derivatives come from going back to the logarithmic definition of the inverse hyperbolic functions and taking the derivative of those. All right. I'm trying to decide what I want to do here. Let me do one example of evaluating, we'll do one example of evaluating an integral using inverse hyperbolic trig functions, and then if we have time, we'll talk about the tractrix. If not, we'll talk about it in just a second. So, questions? All right. So here's our example we want to evaluate. The integral of 2 over x square root of 1 plus 4x squared dx. And I might say something on a test. I might say you can use trig sub, but there's an easier way. And that's your hint that maybe you should, this might be something that you could recognize a different way. So my hint here is we are going to use inverse hyperbolic trig functions. So let's look at this integral and which integral form does this look like? So look back at your integral forms and let's figure out what form this looks like. Which one? It looks like, kind of looks like the that third form. So what would be if we're going to substitute into our formula? What would u be in our formula? 2x, because we have u squared, right? U equals 2x. So du equals 2dx, and a here equals, in our formula, what is it? 1. A equals 1. So then I'm just going to plug into the formula. So we have the integral of du over u over 2 square root of 1 plus u squared. Simplify that, 2 times the integral of du over u times 1 plus u squared, nice and easy. And from the integration formula, this equals minus 2 natural log of 1 plus the square root of 1 plus 4x squared over absolute value of 2x plus c. So this is the kind of thing we would look at this. Now we could get this result from trig substitution. And what I'm going to do is in a separate video I will post to my website. I will do this, I will evaluate this integral using trig substitution and get to this same result. But if we hopefully we have this little developing this little bag of tricks, you might think, I've seen something like this before. It looks like something that maybe I should be familiar with. You look for your inverse trig functions and think it's not quite an inverse trig function. Then you think, oh, maybe it's an inverse hyperbolic trig function, and that could put you on the track of getting to here. And we said that this form was equivalent to, what do we come up with? Cosec. So we have minus 2 cosec of 2x. Yes.
So like if we were to do this one test, how would we go about this if we're not supposed to memorize the
So what I do for quizzes and tests is I allow you one note card. So if it was going to be a test over hyperbolic, the first test, you would have your integration formulas written on your note card. What's that? From back. But again, I'm not going to. My point in doing this is just to introduce you guys to these things, so you have seen them. You know that they exist. You know that they're kind of similar to inverse trig functions, and there's a process for working with them. It's not that I want you that you're going to go forward thinking I'm a master of hyperbolic functions. Just you've seen them a little bit. And they do pop up here and there throughout the semester. There'll be an integral that you evaluate that people always it looks like an inverse sine integral, but it's not quite, and then turns out to be an inverse trig function. So they show up every once in a while in different types of applications. All right, I'm going to stop there for now. So in a separate video, you can access it on my website. You can watch it over the weekend, whatever. I encourage you to watch it so you see the process. I'm going to go through getting this result using trig substitution. And I'm going to go through derive a curve called the tractrix. And the tractrix involves inverse hyperbolic trig function. And what the tractrix is what we have for a tractrix is, it would be like the path if we have a semi-trailer that is turning a corner. So the tractor part of the trailer is moving directly up the y-axis and is connected rigidly to the trailer. The tractrix is the curve that describes the path that the rear wheel takes as that tractor pulls the trailer around the corner. It's called a pursuit curve, and it involves an inverse hyperbolic function. So I want to go through the derivation of the tractrix. Tractrix is an important curve, and it's an interesting application. So I'll do both of those things in the separate video. Watch them at your leisure. Just because it's an interesting application of inverse hyperbolic trig functions. All right, homework. And I'm pretty sure I have it right this time. 390. All right, there you go.